I was looking at this analog device's new components, AD8410A. It's a current sense amplifier. And here is the basic block diagram for this amplifier. And it's basically a difference amplifiers with two branches here and with a gate of 20. And how it works is you have a current flow through a small value current shunt resistor and produce a small voltage here. And the amplifier will take the difference voltage between these two sides and amplify it. And so you will know the current go through this circuitry here. It's a H bridge. And of course, they have many other functions for higher accuracy. And what's really interesting to me is here, this circuitry here. It's a very typical EMI filters for the input side of this circuitry. So you have still have the shunt resistors, and you have this fancy resistor, two resistors, three capacitors, EMI network. Okay, this is the EMI filter network. It's basically the low pass filters in a different ways. And so you can filter whatever the EMI noise came from the shunt or the front end circuitry here, and before the signal goes into the difference amplifiers here. What I'm really want to talk about is these circuitries, how this really works, how this EMI filter works. So I copy this part this part circuitry into here, so we can further analyze. And to better understanding this, let's draw this in a different ways. So we have a resistor R1 here, and another resistor R2, and the capacitor C2 in between, and C1 here to ground, and C3 here connect to the ground. And the input signal come from these two nodes here. And output after the filter, the signal will go into this difference amplifier, basically something like this. If you don't know how the difference amplifier works, you can look at my previous videos. We have multiple videos talk about this. And this part is basically what inside that chip. Okay. And in practice, to make this works better, normally we will have some criteria to choose the R1, R2, and the capacitor values here. Remember to maintain the common mode rejection ratio. It's very important to maintain the components matching between this among all these resistors here. And whatever resistor input you add into the input filters will add to this input resistor here. Or in reality, it could be an op amp or something more complex circuitry here, but it's an equivalent resistor or equivalent impedance, input impedance. This value will add to here, okay? And this will add to the input here. And for the AC signals, the impedance with all these capacitors will also add into this input circuitry here. Okay. So to maintain a higher common mode rejection ratios, in reality, we normally choose this. We have a symmetric configurations. That means R1, R2 are same values. So we can both say that R1 and C1, C3 are same values. So we have C1, C3. Okay. And also R1, R2, R1 or usually R1 or usually small values, something like 10 ohm, and C1 and C2 usually is bigger than C1. So we can talk about this later. Why is that? Okay, for if we have two situations to discuss, and first is for differential input signals. Differential input. Okay. For the differential input signals, and the signal, if we look at this diagram, the signal will go from like this. Okay. So we can draw this equivalent structure here. As the signal the differential signal pass both R1, R2, so we can combine R1, R2 together in series. So we get R1 and R2 here. And C2 is still here, C2. And C1, and this is connected to the ground. This is also connected to the ground, so they are same potential, so they can be connected together. The C1 will be like this, and we'll have another C1 here. So the ground is here, and this side is your input. Okay, so we can basically we can draw equivalent circuitry like this for differential input signals. And this is basically a typical RC filter. So all we need to figure out is what's these values. So this can be further simplified as, and R1 R1 to the same values is 2R1 here, so in series. And C1 is 2C1 in series, and we have this is C1 over 2 combined, and C2 is in parallel with this two C1s here, we get plus C2. Okay, that's a combined capacitance. That will be here, your equivalent C, and the combined capacitance is C1 divided by 2 plus C2. Okay, this now turns into a very simple RC filters. The cutoff frequency FC is 1 over 2 pi times 2R1 times C1 divided by 2 plus C2. Okay. It further simplifies FC equals 1 over 2 pi R1 and multiply 2 into the bracket. We got C1 plus 2C2. Okay, so this is the cutoff frequencies for the differential input signals. Okay, and for common mode, second case is for common mode input. Okay, let's redraw this structure here. We got R1, another same R1, same value R1, and C2, and the C1. C2 and C1 here to ground, and another equal value C1 to ground here. So common mode voltage is equivalent like these two input are short together, and so the signal will flow from the common mode voltage will flow into this both short structure here, then go out from the ground. Okay. And since the same potential here, then you got same potential here, then basically C2 is a short circuit. Okay, so C2, we can replace C2 with a short circuit. And C1s, we could redraw the C1, this C1, go down here. So it's the capacitor, C1, value of C1. So this can be removed. Okay, and then now the FC, these R1, these two are in parallel, so equivalents are R1s are R1 divided by 2, and this C1 and this C1 is in parallel, so it will be it's 2C1. That's the equivalent capacitance is 2C1, and the RC for this RC filter, the cutoff frequency is 1 over 2 pi R1 R1 divided by 2 times 2C1, so it's equals 1 over 2 pi R1 C1. Okay. So this is the cutoff frequencies for the common mode input voltages. Okay, let's put this two cutoff frequencies next to each other so we can see the real difference here. Let's see. Let's see. We have FC differential, FC common, and this is equals 1 over 2 pi r1 um, c1 plus 2c2, c1 plus 2c2. This is 1 over 2 pi r1 c1. Okay, and because c2, as we said, c2 is normally is bigger than c1, that means 2c2 plus c1, 2c2 plus c1 will be bigger than c1. So that means this denominator is bigger, so the cutoff frequency will be lower. So that means if you choose the same value here, as the way we chose the capacitor resistors like what we discussed here, the differential cutoff frequency will be lower than the common mode voltage cutoff frequencies. Okay, let's talk about it about why is C2 need bigger than C1. Remember that for the key, it was for a difference amplifier to maintain a high common mode rejection ratios. We have to maintain this symmetric or this branches between the top branch here and the bottom branch. Okay, and for the C1 here and is other equal value C1 in the other branch, it's very difficult to find the capacitor with exactly same values to have matching values. Okay, and usually 2% is very difficult to get, and normal capacitors like 20% or tolerance, something like that. And if you choose this C1 value, it's in the small values, and basically the impedance for this branch, C1 is 1 over 2 pi omega C1. The C1 will, the impedance with this capacitor will be large. So the voltage divider effect will be smaller. The signal to the op amp will be roughly very close to the signal in here. Okay.